Say that we wanted to combine these two ugly and nasty looking fractions together. How would we go about this? I thought, since that we're on the topic of fractions, and that this is something that came up when I encountered similar scenarios, but instead of just simple numbers, it was scenarios involving equations. In a solid mechanics paper when I was studying engineering, and I thought this would be quite interesting to share. And the reason that I came up with this is because, if you remember from previous video about combining unlike fractions together when they were simple, the butterfly method was sufficient, but I found that when you try to do it with large numbers, the end result, it can be quite inefficient to do, as the numbers are really large. So, yeah, before we deal with this, let's derive the general formula that I came up with by using a very simple example first. Okay, let's try 1 over 6 plus 3 over 2. And how we would add these together is we need to make both the denominators the same. And we do that by multiplying both the numerator and the denominator by 3. I'll write it like this. So it's 1 plus 3 times 3, and both these denominators are 6, so we can write it like this, as one single fraction, as you may know already. And simplifying, we get 1 plus 3 times 3 is 1 plus 9, which is 10, divided by 6, and we can simplify this to 5 over 3 by dividing both top and bottom by 2. Easy, right? Now that we've established the methodology from the simple example, let's start to a derivation. And for starters, I'll keep it in very simple terms, and later we can get more rigorous. The first thing that I noticed was we need a multiplier, and I'll just call this M for now. And what this is basically what you get when you divide the larger denominator by the smaller denominator, which in this case it was 6 divided by 2 because it gave us 3, and then that same 3 was multiplied here. For example, 6 was our larger denominator and 2 was the smaller denominator, and that gave us 3, which we multiplied over here. And then the second thing to know about this would be modifying the fraction. The fraction with the smaller denominator, so modifying the smaller fraction by the multiplier. Oh, whoops, running out of space here, so I'll just bring in a new sheet, a new note. See, we have this fraction here, over the large denominator plus, and we have a small denominator. It had its number, and what we do here is we multiply the numerator by the same multiplier. And small correction here, if I write it this way, it should technically be top and bottom, but then we know that this will result in the one denominator with the large number, because over here, remember 1 over 6, and then we multiplied by 3 in both the numerator and the denominator, and that gave us 6. Both are common, and then we can rewrite it as a single fraction with the 6, which is our large number, as one fraction. This is numerator 1, numerator 2. This would be in 1, the numerator from the large fraction, plus this multiplier times by the numerator of the smaller fraction. That's in very general terms. Let's see if we can tidy up some of this. So let's say n1 is the numerator, and instead of large we can have, let's say, n1 capital, and then the small one will be n2, and we know our multiplier was n1 over n2, and that n1 is greater than n2, because this will be our lowest common multiple, which is always the largest number, and that's why we multiply this divided by that. And simply we can rewrite this as n1 over n1 with capital N1, because we will know that will always result in a single fraction with the larger denominator. Simply n1 plus m times n2. It's a pretty poor choice of letters because n and m they sound really similar, so apologies for that. Hopefully you get my point. It's basically modifying this fraction, the smaller fraction, with a smaller denominator so that it matches the bigger one. Yeah, it really is that simple that I discovered this. That's all there really is to it. So, let's get back to this example here. Okay, at last we can deal with an actual ugly example. So the first step is to establish the multiplier. So I'll just still call it m. Now m will be equal to the larger denominator, and 589 is larger than 127, so 589 divided by 127. Now that we've established what our multiplier is, we can go ahead and modify. Smaller denominator fraction is this 3 over 127, So that's the one that we will be multiplying the numerator by. So this becomes 3 times our m plus, and the numerator of the larger denominator fraction stays unchanged, as we don't need to do anything to it because it's the lowest common multiple. 3m plus 12, and the final denominator of this fraction will be the largest denominator, so that's 589. Substituting this m will give us 3 times 589 divided by 127 plus 12 divided by 589. And without a calculator, we can just leave this as it is. To check, we can use the calculator, and this comes to 0.044 if you write it as a decimal. And if you put 3 over 127 plus 12 over 589 into the calculator, it will give us the same answer. And so this means that this method, or shortcut as I like to call it, is correct. I really hope that you understood this and that I explained it well enough. I hope that made sense and that you found this interesting, and that maybe one day it will come in handy in the future. If you found this video helpful, please subscribe, and as always, thanks for watching, and I'll see you in the next one. Oh yeah, as previously mentioned, I found my old notes from the solid mechanics course that I did, and you can see where I've circled in red. So just ignore the rest. You can see an instance of when I used the shortcut trick to solve an equation. So you can see the 56 and 140. On the left side, you can see that I multiplied the numerator of the smaller denominator by 140 divided by 56, which was our multiplier, and then it nicely combines, making the equation easier to handle and manage, as I mentioned earlier in the video. So yeah, this is a situation where I used it in fractions involving variables.